In this video, I'm going to show you that this area, hang on, I'm going to show you that this green area is always 3 times the size of this red area. And this is our cycloid here, and the equation for our cycloid is given by this. We've seen this in the past. So let me just quickly give you the animation. So we are keeping track of this green point here. We are keeping track of the green point as it moves. So that green point is this bit here. That green point is this green point here. So as it moves around, I'm trying to show you that this green area here is 3 times the size of this red area here. So we need a way of finding out the area of this green area. So the way we're going to do this is, well, we need to work out the area underneath our cycloid. So we need to somehow work out this area, and then we're going to add it to this triangle later on, this triangle, and then that will then give us the green area. But before we do that, let me just remind you of something. So the whole distance here is given by the circumference of our circle. So all the way around here is 2 pi. Is 2 pi radians. But rather than work in radians, in your mind, picture it in degrees. But ultimately, we're going to work in radians. But in your mind, picture it in degrees. So this whole thing here is I know it's 2 pi radians, but let's cut out into 300. Let's imagine we're going to cut out into 360 equal pieces. So just imagine there are 360. So all the way around here is 360 degrees. Now, one increment of t would mean you will increase this by it would mean one increment in the x direction. Another increment of the angle would mean another increment in the x direction. Another increment of the angle would mean another increment in the x direction. So if we're trying to work out this area here, it's really the integral from 0 to t, because one increment of the angle means one increment in the x direction. Another increment of the angle would mean another increment in the x direction. So by the time it gets around here, this thing here will be t. So we are integrating from 0 to t. So we are trying to work out this green area here. But we're going to work out the area underneath the cycloid. So we're going to work out the area underneath the cycloid from 0 to t, from 0 to t, and then later on. So we're going to call this the left green. Later on, we're going to have to add it to the right green. So for the time being, let's just concentrate on the left green. The left green is given by this. Remember, if you're trying to work out the area underneath a parametric curve, in your mind think of it like this. Hang on. In your mind think of it like this. So when you do the integral, let's say whatever here. So in your mind you should picture this. Each step of the way you need to know the height. Each step of the way you need to know the height. Well, the height is given by this. The height is given by this. But then you need this dx. Well, dx, to obtain this dx, you need to differentiate this. So you differentiate this. So dx equals r, and then minus r cos t. So and then dt. So we can then put this whole thing into the dx. That will then give us this thing here. So we are integrating from 1 to t. But here's a problem. We are integrating from 1 to t. Sorry, from 0 to t. But here we're doing it with respect to t. Now cast your mind back to when you were trying to understand the fundamental theorem of calculus, where you're trying to understand the area underneath a function f of x. So you're trying, but the problem is you're trying to reserve this x. So this x can slide back and forth. So you're trying to create a function where you insert an x, and then it should spit out the area. It should spit out an area. But the problem is this f of x here. Well, you're trying to use well, at the moment the two will clash because you're using this x to represent something that you can slide back and forth, but then the function is in terms of x. So when you were trying to understand the fundamental theorem of calculus, you had to create this function here, this capital F of x equals this thing here. We did this in the past, where this x is reserved for well we can slide this x back and forth here, but then this x here would clash with this x here. So the way we got around this was by calling this function f of t and doing it with respect to t, but the function stays the same. It's just we want to use this x to represent what we put into the function. Well, the same is true here. We want to reserve this t. So we are trying to create a function where we insert a t and then it should spit out the area. But the problem is our function, this thing here is all in terms of t. So the way we would get around this is to call this t something else. Let's call it u, just like what we did up here. This is our function f of x, but we call it f of t and then dt, and then we reserve this x to represent the input. So now we're trying to do the same thing. We are trying to create a function where we insert t and then it will spit out an area. But the problem is this is in terms of t. So let's call everything u. So it will be cos of u. We are just changing the name, and then so that we can use this t to represent our variable. So we can input t and we spit out an area. So this thing here would be u, this thing here would be u, and then dt would turn to du. So now we in a way created something like this, where we insert a variable t, and then well, the area, this area here, hang on. So this area here from 0 to t is not given by this, but given by this. Okay, from 0 to t. I will continue in the next video. Okay.